So looking again at this example, which of these simple graphs has a Hamilton circuit or if not a Hamilton path? And so I redid the solution, and I didn't go in the order G1, G2, G3. I instead went in order from easiest to hardest. All right, the easiest one is G3. G3 has a very, very simple Hamilton circuit, right? Just go along the outside, right? So that's definitely the easiest one. G2 also has a Hamilton circuit, although not as, well, no, I guess that one's pretty clear too. I think for G2, no, you can, there's a bunch of different places you can start. So I started in the middle for some reason, and I went this way. Okay. But you could start at any of those points and just trace the same path, right? You could start from A and go like this. Okay. Does that make sense? All right, now G1, I remember I started with G1 last time and I said, well, it definitely has a Hamilton path, right? Like you can do a letter Z, and that's a Hamilton path. Does it have a Hamilton circuit? We said no. But I thought it would be nice to show you sort of a slightly more rigorous argument why there isn't. Okay. So the explanation could go something like this. The reason that G1 doesn't have a Hamilton circuit is because each of these four vertices has degree 2. That means that both of the edges that are incident with those vertices would have to be included in a Hamilton circuit, right? And that's because, you know, one edge in, one edge out. Does that make sense? You're trying to visit each vertex exactly one time. All right, so since those have degree 2, you would have to use both edges. Okay? And on a related note, this might come in handy in a homework problem. Any graph that has pendant vertices, you know, degree 1, automatically can't have a Hamilton circuit, right? Because how would you get to that vertex, right, and back? You would have to trace over the same edge more than once. And that's cheating. Can't do that. Okay, so each of these outer vertices has degree 2, which means that you have to use both edges. And that means that every edge in the graph would have to be included in a Hamilton circuit. Okay? And that's a problem because vertex E has degree 4, and all 4 edges here would have to be included, and clearly that's impossible. You will not be able to trace these 4 edges without hitting E a whole bunch of times, right? Does that make sense? Okay. So that's why you can't have a Hamilton circuit, but you can have a Hamilton path. For example, the letter Z. Okay. Make sense? Okay, the other thing that I noticed when I was going back over this, and I did not notice this in class, and I kind of feel like doing this. I had a wrong word on this next slide. That used to say necessary conditions. These are not necessary conditions. They're sufficient conditions. All right? So we said no simple necessary and sufficient conditions are known for the existence of a Hamilton circuit the way they are for Euler, and I see a word spelled wrong. For Euler, there's a very simple necessary and sufficient condition. You have an Euler circuit if all the vertices have even degree, right? Okay, but there are some sufficient conditions. So the reason these are sufficient conditions is because it's saying if the graph has this property, then the graph has a Hamilton circuit. That is a sufficient condition. It is not a necessary condition. Not a necessary condition. All right, for example, a C5 cycle with 5 vertices is very clearly Hamiltonian, but all the vertices are degree 2, which is less than n over 2. All right? It's saying if all the vertices have degree at least n over 2, then you're guaranteed to have a Hamilton circuit, but you don't have to have that. And here's an example of where you don't have to have that. This has 5 vertices. N over 2 is 2.5. All the vertices are degree 2. But there's a Hamilton circuit there, right? Just trace over the whole thing. Okay. All right. And then Orr's theorem, which says that if you check any pair of vertices and their degrees add up to at least n, then you're also guaranteed to have a Hamilton circuit. And Peter, you were asking about a proof for Dirac's theorem. And so I noticed that they actually outline that in one of the homework problems, which I didn't assign. But if you're interested, it's actually the outline of a proof of Orr's theorem. And then once you have a proof of Orr's theorem, Dirac's theorem is just a corollary because let's say that you've proven Orr's theorem, okay? And then you look at Dirac's theorem, you would just say, okay, suppose that my graph has all vertices degree at least n over 2. Well then, you take any 2 of those vertices and they're going to add up to at least n. So this is a special case of this. All right? And so if you can prove Orr's theorem, then you sort of get Dirac's theorem for free. All right? So anybody who's interested in seeing the proof can check that out. All right. I think those were the 2 things that I wanted to correct in 10.5. And here's the traveling salesperson problem. So they've made it, politically correct. Traveling salesperson problem asks for the shortest route a traveling salesperson should take to visit a set of cities. And so that reduces to finding a Hamilton circuit so that the total sum of the weights of the edges is as small as possible. And we're going to talk about weighted graphs more here in a minute. Okay, and then here's another application, a family of binary codes known as gray codes, which minimize the effect of transmission errors, correspond to Hamilton circuits in the n cube. Remember the n cube? So Q2 is like this. The subscript sort of tells you the dimensions of the cube. So this is 0, 0, 0, 1, 1, 0, 1, 1, and then 2 vertices are adjacent if and only if they have exactly 1 different bit. Okay, so just some of the applications. All right. That's it for 10.5. Yeah.
So it's a path if it goes through every vertex.
What kind of path?
Oh, it's a Hamilton path through every vertex, but it's a Hamilton circuit if it does its
Yeah, and so the only difference is a circuit begins and ends at the same point. Well, except for the beginning and ending point. Yeah.
Okay, so it would be a Hamilton circuit through by a straight line. It would be a Hamilton path through by a straight line.
A straight line could be a Hamilton path, as long as it visited every vertex.
Okay, so every Hamilton circuit is a Hamilton path.
Correct. That's right. Yeah. A circuit is a special kind of path that has the same beginning and ending vertex.
So revisiting the first point is true effect.
That's that. Yeah, that's okay. Yeah. Yeah. Euler.
Euler, an Euler path that goes through every line,
Every edge.
every edge, whereas an Euler circuit,
So yeah, Euler is edges, right? An Euler path is a path that traces every edge exactly one time, okay? And an Euler circuit is an Euler path that begins and ends at the same vertex. So a circuit begins and ends at the same vertex. A path doesn't have to. It can, but it doesn't have to.
so would every Euler path be an Euler circuit?
No, but every Euler circuit would be an Euler path. Every circuit is a path.
Oh, so it's both.
No, it's the same for both. Every circuit is a path,
Oh.
right? A circuit is a path in which the beginning and ending point are the same.
Path is the term.
Right. A path is the general term for a circuit. Exactly. All right. Good stuff. All right, so the next thing is, and you have this on Blackboard now, you didn't have it the other day. Sorry about that. Okay. Some of this we already looked at. We already looked at this. So these were the examples of using Dirac's theorem and Orr's theorem. So we already looked at those, right? Already did this. Already did this. And I think those were the only things we did from this thing. Okay. So this is actually going back to 10.4. 10.4. 10. Maybe it was 10.3. It was one of those. All right. So remember we were finding isomorphic, determining whether graphs were isomorphic. All right. Isomorphic very roughly, loosely says that the two graphs are basically the same. All right. Except for somebody's changed the names of the vertices and maybe the arrangement of the vertices, but other than that, they're the same graph. Okay. All right, and so there are some useful tricks that you can take advantage of for finding isomorphisms. And I had mentioned this the other day, but didn't show you an example of it. All right, so if you have a path in your first graph, your mapping, all right, remember the mapping is you have a list of vertices and you say this vertex goes here, and this vertex goes here, and this vertex goes here. So when you map that path over to the other graph, it also has to be a path there. And the same thing for circuits. All right, circuits in the first graph have to be circuits in the second graph. So now I'm going to use that to try to find an isomorphism between these two graphs. Okay, and perfect. Okay. So if you have this up on your screen, you'll be able to see it. Can't see it really well if you're just looking up here. So the first thing I'm going to do is I'm going to stare at these two graphs, and eventually I notice that each of those two graphs has a couple of 4 cycles in it. In this graph, there's a 4 cycle here, right? And there's also a 4 cycle here. In this graph here, the 4 cycles I think are a little easier to see. There's one here and one here. Okay? So how that helps me is that in each graph there are exactly 2 vertices that are not part of a 4 cycle. When you look at this one and this one, these are the only 2 vertices that are not part of a 4 cycle. And when you look at this one and this one, these 2 vertices are not part of a 4 cycle. So what that tells me is that an isomorphism, if there is one, has to send these 2 vertices to these 2 vertices. Because that property is invariant under an isomorphism. Okay? So U1 and U8 have to get mapped to V2 and V6 in some order. Okay? And that's really helpful information because if I didn't notice that, well, I'd have 8 guesses where to send U1, and I would have 8 guesses, or I guess 7 guesses where to send U8. All right? But now I only have 2 guesses for each. So I'm just going to try something. I'm going to try sending U1 to V2, and I'm going to try sending U8 to V6. All right. I might want to scribble on this, so let me do this. Okay. Oops. All right. So, now I'm going to start looking at neighbors of U1 and U8. I'll start with U1. So U1, well, has U8 as a neighbor. That's one of its neighbors. And V2 and V6 are also neighbors. So far that's okay. Neighbors have to get mapped to neighbors. All right, the other neighbors of U1 are U3 and U2, right? U2 and U3. Okay, so they have to get mapped to neighbors of V2. U2 and U3 are adjacent to U1. V1 and V3 are adjacent to V2. So these 2 vertices have to get mapped to these 2 vertices. So I'm just going to try sending this one here and this one here. You know? What's that? Do it on the, well, maybe if I, you know what, I'll move this over here. Wish I could make it bigger. I could, right? Oh, can you do that? I don't know how to do that. Oh, okay. Yeah, there we go. And then when we, yeah, okay, that's good. Thank you. Okay, so let's see, where were we? So by doing on the figure, you mean like this. U1 is going to V2, like that? Okay. U1 is going to V2. U8, where is U8? This is U8, right? U8 is going to V6. Okay, and now we're going to try sending U2 to V1 and U3 to V3. This is V3. Okay. The other way that I do it is when I'm actually listing these mappings is I'll start, I kind of do the, I don't know what to call it, the reverse of what I'm doing there. I'll just start connecting my vertices on the list. Okay. All right. So let's see if this checks out so far. U1 has neighbors U8, U3, and U2. All of these guys. So that means V2 has to have these 3 neighbors, and I think it does. V2 is adjacent to V1, V3, and V8. So that seems okay so far. Right? Did I read it wrong? Oh, V6, V1, and V3. Oh, right, this is V6. Okay. All right, so then the next thing I noticed was that U4, which is the only other neighbor of U3 that hasn't been mentioned yet. Here's, is that true? Which one is U3? This is U3. U3 is adjacent to U1, U2, and U4. Okay. So we've talked about U1 and U2, but we haven't talked about U4. And the counterpart of U3 we think is V3. And it has one other neighbor, which is V4. So U4 is going to have to go to V4. Assuming all of this is okay. All right, so that leaves us with 3 other vertices, and let me see if I can try to talk you through how I figured out how that should go. So we're left with U5, U6, U7, and over here we're left with V, 1, 2, 3, 4, 5, 7, and 8. Okay. All right, so how is this going to have to go? Well, let's see, where is U5? This is U5. U5 has as neighbors U4, U6, and U2. So we've talked about U2 and U4. Okay. All right, so the counterpart of U5 is going to have to be a common neighbor of V1 and V4, and I think we can figure out what that would have to be, right? Here's V1, here's V4. They have a common neighbor at V8, right? And I think that's their only common neighbor, isn't it? V1 has neighbors 2, 3, and 8. V4 has neighbors 3, 5, and 8. So 5 has to go to 8. And then 6 has neighbors 5, 7, and 8. We haven't talked about 7 and 8. We've only talked about 5. All right. So so let's see. Out of 5 and 7, well, 8 is adjacent to 7. It is not adjacent to 5. U6 is adjacent to U5. So whatever we send U6 to has to be adjacent to V8, and that has to be V7. Okay, and now I think I know where U7 goes. U7 has to go there. Okay. So those two graphs are isomorphic. They are essentially the same graph. Essentially the same graph. They have all the same properties. Same number of vertices, same number of, same degrees, same degree sets, same kinds of cycles, all that stuff. All right. So I'll let you play with that. I assigned not a whole number of those or a whole bunch of those because they can be a little time consuming. You have to play with them. The ones that go quicker are the ones that are not isomorphic. If you can see that, oh, wait a minute, one of these graphs has a triangle in it and the other one doesn't, all right? Then that's all you have to say. Okay? They can't be isomorphic. All right. So, you ready for questions? Questions? Yes?
So the V graph would, technically speaking, it would just be a U graph with the points shifted around.
Yeah, with the points rearranged somehow.
So what's important is recognizing the neighbors.
Yeah, the neighbors and the types of circuits that it contains or cycles.
So you basically recognize the neighbors, you set them up as groups, and you kind of work down with that.
Yeah. It's like a big logic puzzle almost. All right. So did that, and so that brings us to this. Okay. Dijkstra's algorithm. Dijkstra's algorithm is a way, of finding a path in a weighted graph. So a weighted graph, by the way, is something that looks like this, all right, where you have a bunch of vertices, and each edge has a weight assigned to it. So that weight could represent a distance. It could represent a cost, some kind of cost. Could represent a speed. It could represent, a bunch of different things. So what Dijkstra's algorithm does is it gives you an efficient way to find a path of least weight from one vertex to another vertex. Okay. All right, so here's the idea how it works. I'm not going to try. Your brains likely work better reading stuff like this than mine does. I stole this from Wikipedia. And I can tell you from my own experience, there are lots of good YouTube videos on this. All right. The first time I taught the class last year, I had not done Dijkstra's algorithm myself. Let's see, last year was 2015. I hadn't done it since 2002 was the last time I got to teach it. So I did not remember how it worked. I had to brush up. Okay. But essentially the idea is that you start with the vertex that you need to start at. The ending point isn't even really that important because as you work through the algorithm, it's going to give you the shortest paths from A to all the other points, really. Okay? So the idea behind the algorithm is that you start at wherever you want to start at, let's say A, and you figure out, okay, what are the, where can I go from A? All right? And then each time you visit a vertex, you add that vertex to what we call your visited set, your set of vertices that you have visited. And then your next vertex is going to be the one that is the shortest distance from where you're at. Okay, let me show you. Okay. So I remember from last year, I wanted to try to find a better way to do this than, the way we did it last year was okay, but I found that people were getting a little confused and making a certain type of mistake a lot, and I was actually making the same mistake sometimes. So what I figured out was it might be a good idea to do what I did last year, which was to make this chart and also scribble some stuff on the graph. I think doing both of those things is helpful. Okay, so what I'm going to do across the top is list all of my vertices, and it really doesn't matter in what order. Okay. And then down the side is going to be the visited set. These are going to be the vertices that I visited. Okay? All right, so the first step is to start at A. So that's your first visited vertex. And then you see where can you go from A? Well, I can go to B or I can go to C. All right, so under A, I'm going to write 0. And I'm going to put a little subscript that tells me where I just came from. Okay? And then, after this step, we're not going to look at A anymore because we've already been to A. Obviously, no shortest path is going to go to A and then go back to A, right? We're done with A. I can get to B with a length of 2, and I can get to C with a length of 3. And I cannot reach any other vertex directly from A. So initially, those are going to be set to infinity, which means they're unreachable directly from A. Okay. Now, here's the extra thing that I didn't think to show the class last year. You might find it helpful to actually mark on your graph those distances and then update them as we'll update them if we find shorter ways to get to those points. Okay? All right, so now, out of all the vertices that you have not visited, you pick the smallest distance, which is a 2. So that means the next vertex that I'm going to add to my visited set is B. Okay? So now I'm at B. All right, well, it's 0 units from B to B, so that's not going to change that distance, so that's still 2 units coming from A. I cannot go from B to C, so the shortest way to get to C from A is still 3, and that's still coming from A. I can get from B to D, okay? And so this is where I think it's helpful to look at the graph. It took me 2 units to get from to vertex B. It's going to take me another 5 to get to vertex D. So now D is reachable. It's reachable in 7 units. So we're going to put a 7 subscript B there. So we have found a shorter distance to D, okay, which didn't take much, right? Earlier D was unreachable. Okay, and I can also get to vertex E from B. It was 2 to get to B. It's another 2 to get to E. So that means I can reach E in 4 coming from B. And I still cannot get to Z, so that's still infinity. Coming from, it really doesn't matter. Okay. Does that kind of sort of make sense? So what you're doing as we go along is we're going to keep updating all these vertices, and then once we have visited all the vertices, we will have a list of what is the shortest distance to each vertex. All right? So basically at each step you're making a choice. Is the way that I already knew how to get to that vertex the best way, or have I found a better way? And if you find a better way, then use that way. And if the new way is not any better, then don't use it, just use the old way. Okay. So now we have visited vertex B. I am done with B. And so out of the ones that are left, I'm going to pick the smallest one, which is at C. So I'm going to add C to the visited set. Okay. And then I'm going to be done with C. So once I put a box around something, you're done with that column. Okay? So from vertex C, which took me 3 to get there, I cannot get to D. So I cannot improve the distance to D by going through C. So we're just going to carry this down. Let's see. I can get from C to E in 3 plus 5 equals 8. But that's not an improvement. I had already found a way to get there in 4. So I'm going to keep the 4. And I cannot get from C to Z. And so we still have not found a way to get to Z. Right. Okay. I'm done with vertex C. So now I look at the remaining distances of the unvisited vertices, and the next one is the 4. So that's at vertex E. Okay, so we're running out of unvisited vertices. Okay, I got to E in 4 steps. I can go to D in 1 more step, and that's an improvement, right? Earlier, the best way I had found to get to D was 7, and now I see a way to get there in 5. So we're going to go to vertex D in 5 units coming from E. Okay, E to E, this is done. Oh, and now I can finally get to Z, right? Took me 4 steps to get to E. It takes me another 4 steps to get to Z. So finally I can get to Z in 8 steps going through E. All right, so 2 unvisited vertices left, D and Z. So I'm going to take D because that's the smaller one. And I'm going to think about going from D to E. No, I'm not. I've already been to E. Oh, just to Z, right? So we got to D in 5 steps. I can get to Z in 2 more steps, and that's an improvement. right? All right, so out of all the unvisited, there's only one left. You now have your shortest distances to not only z, but to all the other vertices. Okay.
So for A, okay, so the top row lists how to get, no, the V lists the starting point.
Yeah, the V is really a column label. Let's do it like this. Yeah, that's unclear. I could have, yeah.
Okay, so V lists the starting point.
V lists the visited set. So those are the set of, this whole column is the visited set. Okay? So you start where you want to start, which in this case was A, and you calculate your distances from A to all the other vertices. And then you just keep going through and looking, okay, which one of those is the smallest? That's where I'm going to go next. And then I'm going to see if I can improve any of those other distances by going through that new vertex.
Okay, so the reason why, okay, it's 0 by A, it's going from A to A.
It's going from A to A.
And going from A to B is 2A, correct?
It's 2. Yeah, and the subscript is just telling me where did I just come from.
Oh, so the reason why D is infinity is indicate that you can't go to
I can't get directly from A to D.
for B is B to B is still 2. Okay.
If you're writing a program for this, this is really hardcore. I skipped this step. The first step in a computer program for this is actually to set this distance to 0 and all the other distances to infinity. That's the very first step, and then you do this, right? And it's kind of an iterative thing. You just keep comparing which is smaller, the distance from the current vertex or the distance that I had calculated in the previous step. You just compare those two and then pick the one that's smaller.
Oh, I see. So the reason why everything is, okay, now I get it. The reason why everything is gone is because you're maintaining the step count.
Mm-hmm.
Okay.
Yeah, so the thing that we kept forgetting to do last year, I don't know if you remember, I wasn't keeping track of them up here. And then when we went to calculate the new distances, it was really easy to forget that you had to, like if you were going from B to D, we kept wanting to say that distance was 5 instead of 7 because we kept forgetting to include the distance that we had already gone. Okay. And I'm finding this really helpful for not forgetting to do that. Okay. And then the other thing, okay, so it's not hard. I mean, this is a small graph. Using this method, and this is where the table, I think, comes in handy. The table helps you keep track of, okay, if I'm interested in going from A to Z, that distance, shortest distance is 7. And then what was that path again? Well, it was to go from A to B. It was to go from A to B, from B to E, from E to D, and then from D to Z. And you can trace that. I'm trying to remember how we did this part. Because in a bigger graph, it might be difficult to keep track of that. Well, it's not over here. A to B. Oh. Right. Thank you. I couldn't remember. That was the one part I couldn't remember. Okay, so ending at Z, you look there, you go to D, that tells you E, you go to E, that tells you B, you go to B, that tells you A. That's how it works. All right. Kind of, sort of. Hmm?
Can you go back to this?
Oh, you want to see that big thing? Okay. Assign to every node a tentative distance value. Set it to 0 for the initial node and to infinity for all the other nodes. And by the way, I noticed that if you Google Dijkstra's algorithm, to find resources and stuff, there's pseudocode all over the place for this. Okay. Set the initial node as current, so think of current as the vertex that you're at, and mark all the other nodes unvisited. Create a set of all the unvisited nodes, called the unvisited set. For the current node, consider all of its unvisited neighbors. Calculate their tentative distances. So tentative distances is just what would be the total distance going from this point. Now the tentative distance is not necessarily the shortest distance. Okay? So that's why you have to compare the tentative distance to the current assigned value. All right? And then just pick the one that's smaller. For example, if the current node A is marked with a distance of 6 and the edge connecting it with a neighbor B has length 2, then the distance to B through A will be 8. If B was previously marked with a distance greater than 8, then change it to 8, otherwise keep it the way it is. Okay. When we're done considering all the neighbors of the current node, mark the current node as visited and remove it from the unvisited set. And then you continue until every vertex has been visited. Right? Okay. Any other questions? I have another example. Oh, you know what? I'll put up the other example and then we'll take a break. So notice this is just stolen from good old Wikipedia. Okay, so now we're trying to find the shortest mileage between Boston and San Francisco. Two cities are connected by an edge if there's a way to get from the one city to the other. So like if there's a flight from the one city to the next, direct flight. Okay, so let's see. I guess we can work with that, right? Okay. So down the side is going to be my visited set, and across the top I'm going to list the cities in any order. It doesn't matter. So I'll just go from left to right. So we're going to go San Francisco, LA, Denver, Chicago, Atlanta, Miami, New York, Boston. Okay. So the first city I'm visiting is Boston because that's where I'm starting. Zero miles to Boston, so we're done with Boston. We won't be going back to Boston. From Boston, you can only get to New York or Chicago. So New York is 191 miles from Boston. Chicago is 860 miles from Boston, and every other city is unreachable from Boston. Right? So from the set of unvisited cities, the shortest distance is New York. So that's where I'm going to go next. And from New York, we can get to a whole bunch of places. Oh, I just noticed something. I can't write on that. Oh, okay. Thank you. And maybe make the... Okay.
I can't move that home.
Well, you can. We haven't done a lot with it. I was just going to say if you could make the...
Smaller?
Well, if you can make the chart transparent, then, well... Yeah, maybe just make the chart a little smaller, I guess. Or... How should it work?
You can make it smaller. Okay.
Yeah, keep it at the bottom.
You can just leave it in this one.
Okay. Oh. Okay.
Instead of, sliding.
Right, right.
That works.
Yeah, that works. Okay, we can fix this real quick. Okay, go to Boston first. 0 miles to Boston, 191 miles to New York, 860 miles to Chicago. These are all unreachable. Okay, so then the smallest distance is New York, so I'm going to go there next. And from New York, I can get to a whole bunch of different places that I haven't been before. I can get to Miami, which is 1,090 miles. So let's see, I want to do this, right? I want to mark New York 191. I want to mark this like that, like that. This is 860. This is this, and this, right? That's what I wanted to do. Okay. So now from New York, I can go to, I've already gone 191 miles. In another 1,090 miles, I can get to Miami, and that's definitely an improvement. That is 1,100 plus 191 is 1,291. Is that 1,281? 191 plus 1090? 1281 if you come from New York. This one is done. And where else can we go? We can go to Atlanta. We were never able to go there. That's 191 plus, does that say 760? Yeah. Okay. Which is 951 from New York. We can also go to Los Angeles. We've already gone 191. Another 2451 is 2642, right? And okay, so now we can also go to Chicago. However, that is not an improvement over what we already have. We were already able to get to Chicago in 860. Going through New York would be 191 plus 722, which is bigger. So we're going to keep the current value for Chicago. You would just go there from Boston. You cannot get from New York to Denver. You can get from New York to San Francisco. So it was 191 from Boston to New York. It is another 2534 to San Francisco. That's a total of 2725. Right? So far, so good? Okay, so out of the unvisited, the smallest is Chicago. So we're going to go there next. So where can we get from Chicago that we haven't already been? We've already been to New York. We've already been to Boston. Now I forgot to update these. Okay. Right? We've already been to New York. We've already been to Boston. We've already been to Atlanta, and this is not going to be an improvement, right? 860 plus 606. That's a lot bigger than 951, so we're going to keep the value for Atlanta. We can go to Denver finally. Hooray. That says 908. So it's 860 plus 908 is 1768 going through Chicago. We can go to San Francisco. 860 plus 1855. If I remember correctly what happens. Is 10 miles better than what it was. So we'll take it. 2715 if we go through Chicago. And that's all of them, right? Because the other one was Atlanta. No, there was one more. Is there one more? San Francisco, Denver, Atlanta, New York, and Boston, and we've already been to those. Okay. So far, so good? Out of the remaining ones left, we're going to go to Atlanta next. And from Atlanta, we can go 3 different places, but we've already been to New York and Chicago, so the only one we're going to look at is Miami. And we're not going to do anything with that because it's currently 951. And I don't want to add another 595 because that's going to be bigger than 1281. So we're going to keep the current value for Miami. Oh, you know what? It doesn't matter all that much, but oh. Yeah, okay, so you notice that some of the cities that were reachable before are not reachable from Chicago. That technically means that you're comparing the current value to infinity. So you would keep the current value. I usually like to bring those down. Okay. All right. So Atlanta to Miami, that is not an improvement over what we already have for Miami, so we're going to keep what we already have. And the only other 2 places you can go from Atlanta are places we've already been, New York and Chicago, right? So we're not going to go back there. So we're going to keep these. Okay. We are done with Atlanta. So next we're going to go to Miami. And nothing interesting is going to happen in Miami because the only places you can get from Miami are Atlanta and New York, and we've already been to those. Okay. So now we're going to go to Denver. I don't think I have enough rows. From Denver, you can go to Los Angeles. I forgot to update one thing. This is now 2715, right? From Denver, you can go to Los Angeles. Current value, and I never updated Denver either. This is a new thing that I'm trying to get used to. All right. Denver is currently 1768, adding another 834. Is that what that is? Actually, I think is a little better, isn't it? 1768 plus 834 is... Is that right? Okay, so that's an improvement. 2602 through Denver. You can also get from Denver to San Francisco, 1768 plus 957, which is just going to be a little bit too big, isn't it? 1768 plus 957, interestingly, puts you back at 2725. Which is where we used to be, but we improved it. So we're not going to change that. We're going to keep that. All right. Almost there. So now the smallest value is LA. 2602. And I believe you can get from LA to San Francisco. What does that say? 349? I don't want that, right? We're at 2602. If I add 349, that's going to put me like over 2,900. So I don't want that. I want to keep 2715. Okay. So now we're done. So the shortest distance from Boston to San Francisco is 2715. And let me see if I can do this. The route is end at San Francisco, from Chicago, from Boston. So just Boston to Chicago to San Francisco. Is that making more sense? Oh, yeah. And there are other ones on YouTube of varying quality, right? Yeah. You know what? If I think of it, I actually have a little downtime after class until I have to go to a meeting at 4. I'll maybe post a link for the one that I liked. The one that I liked did not use the chart. I stole that idea from somebody else. But he had a good, he explained it well. And he just did it, he just did this. And he actually did it on a computer, so he would, instead of crossing them out, he would just delete them and replace them with the smaller number. Okay. Yeah. All right, you guys, so let's see who took in any of that. Yes, you're going to do it. Okay, so now it's not about the least amount of mileage, it's about the cheapest. I like these airfares. All right, so the easiest way for you is just put it up on your screen. So the least expensive combination of flights connecting Boston and San Francisco. While you're looking at that on the screen, I'm going to set up the next, actually, no, I've got it all done out on there. So what I'm going to do is I'm just going to make another insert like that.
So all of these problems that have prohibitively expensive amount of paper all these problems that have a prohibitively expensive amount of paper.
No. You can do it on,
Excel?
I mean, just in the amount of paper it takes to hold the chart, really.
Yeah, because I was considering doing it on Excel
Oh.
because of how much I've had, because of how hard it is to actually do Excel.
Oh, to draw the graph. Yeah.
It just takes forever to draw down all the boxes and all the numbers.
Yeah, you can do it on Excel.
So like when I do it, like, I can just do it on Excel, print out the.
Yeah, yeah.
I really don't want to.
All right, ready? So we're trying to find the cheapest way to get from Boston to San Francisco. So we're going to start in Boston, which means we are done with Boston. I noticed one of the YouTube videos I liked, he was doing it on the computer, so instead of putting a box around the one that he was done with, he would just change it to a different color, like blue. All right. So from Boston, this must be the same airline as the last example. You can only get to New York for $39. Or you can go to Chicago for $79, right? And I know there's an infinity in here somewhere. Why don't they make this searchable? Looking for mathy stuff. Where are you, infinity? Okay, I either missed it or... Yeah, we could, or we could do it like this. Okay. All right. You don't really need to put the tag on a infinity, but that's okay.
Take it back. trying to work this graphics, I marked the wrong word, just right.
Okay, New York 39, Chicago 79, everywhere else infinity. Right? Okay, so the cheapest place to go from Boston is New York, so we'll go there next. So we're going to bring this down and then turn it blue. La da 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 dee. Okay, so from New York, which has already cost $39 to get there, remember, you can go to Miami for another $99. So that's a total of $138. You can go to Atlanta for another $79 for a total of $118. And you can go to Los Angeles for another $129 for a total of $168. Right? Is that all of them? We don't want Boston again. Miami, Atlanta. Oh, and we haven't been. Oh, we have been to Chicago. Is this a cheaper way to get to Chicago? No. Right? It's 39 plus 59. That's more than 79. So we're just going to keep this. We still can't get to these places. Okay. So out of the places that we haven't been, the cheapest one is Chicago. So we'll go there next. All right, so no more New York, no more Boston. Let's see, how much is, oh, so we have to update the map. We were able to get to Miami. We were able to get to Atlanta. We were able to get to LA. Is that it?
I think you go from New York to San Francisco.
Can you?
Yeah, there's on top of the 120.
Oh, thank you. I didn't even see that. So that's another 168. Okay. Right? Okay, so now we're in Chicago. From Chicago, we're not going to go back to Boston or New York. We could try going to Atlanta, but that's going to cost $79 plus $99, which we don't want to do because we can already do it for $118. Where else can we go? Oh, we can finally go to Denver. So it cost us $79 to get to Chicago. It costs another $69 to get to Denver. That's a total of $148. Right? And you can also go from Chicago to San Francisco. It costs $79 to get to Chicago. Another $99 would make that $178. So we don't want to do that. You can't go from Chicago to LA. And you can't go from Chicago to Miami. Okay. So far, so good? Out of the places we haven't been, the next cheapest one is Atlanta. Okay, so where can we go from Atlanta? We can go to Miami It cost us $118 to get to Atlanta. It would cost another $69 to get to Miami, and that's more than $138. We're not going back to Chicago. We cannot go to Denver. We cannot go to LA. We can't go to San Francisco. So those are not going to change. Right? Cheapest one of those is Miami. From Miami, I don't think we can go anywhere we haven't already been, right? So now we're going to go to Denver. We can go from Denver to LA, but it's going to cost $148 plus $89, which we don't want to do. And we can go from Denver to San Francisco, but that's also going to cost $148 plus $89, and we don't want to do that. Okay. All right, so then what if there's a tie? If there's a tie, you can just pick either one. Might as well pick San Francisco, right? So I think because we picked San Francisco, I think that means we can, well, that means we can skip visiting LA, right? Well, I mean, we would skip it anyway. It costs $39 to get there. We could have just gone there right from New York, so you would keep that. Essentially, at this point, you're done. If you're trying to get to San Francisco, make it official. Just do this. Okay. Because then, if the next question is, you know, what's the cheapest way to get to LA, you already have the answer. You don't have to do it again. Well, you tell me. So we wanted to go to San Francisco. Where were we just before we were in San Francisco? New York. Where were we just before New York? Boston, right? Yeah, so you just go Boston to New York to San Francisco. $168. All right. And
So basically, if the path exceeds the amount of your previously most efficient path, you can just scrap it.
just keep the one you already had. Yep.
Do that, you can make this
Mm-hmm. All right. Let's see. So there's that. That's the same thing. Oh, yeah, I didn't even bother with, yeah. Okay. So I remember last year we probably had, because remember, today is the last day I'm going to do anything new. This is it. On Tuesday, I'm going to turn this off.